Okay, so here we've got an example problem for more complex systems of forces and Newton's law. I really like this one because it's got everything. It's got an inclined plane. You're rotating in this problem, so you've got centripetal force. There's friction. What more could you ask for, right? Okay, so the first thing we're going to do is we're going to make a free body diagram for this guy. And free body diagram, so we have the weight pointing down, always points straight down. The normal force points normal to the surface. Okay, and then he would slide were it not for friction, so friction must be pointing opposed from the direction he's slipping. Now, this problem says, if you read it, it'll say he goes at a speed of 3.75 meters per second, right? Now, we know that in order to go in a circle, you need to be accelerated toward the center of the circle. So you might wonder, well, what's accelerating him in this direction? The component of friction points in the centripetal direction. And so that provides the centripetal acceleration. The question is friction strong enough to create a centripetal acceleration big enough to handle this speed? Remember, centripetal acceleration is v squared over r. So the bigger you make v, the bigger the acceleration has to be. So we're going to solve for this problem. We're going to figure out what speed friction is able to provide, and we'll see if it's the same speed as this. If the speed friction is able to provide is bigger than this, then no problem. If the speed is smaller, that is a problem. Remember that whenever we have static friction, and we say that it's equal to mu times the normal, we really mean that that's the maximum force that static friction is able to provide. And so whatever v we solve for will be the maximum speed. As far as free body diagram, that's it. There's really only three forces in this problem. It seems much more complicated because he's sliding and spinning and all sorts of other stuff. But as far as writing our equations, we just do that. And then I've already started to do it. We want to start to break this into components, sensible components. And he has to accelerate toward the center of the circle. And I'll call that the centripetal direction. But we don't want him sliding up or down. So that means that if I have two components, I'll just say, here's the centripetal direction, and then I'll call the other direction the y direction. We want ay equals 0, and we want the centripetal acceleration to be v squared over r so that he can go in a circle. Okay, so let's see. The angle given in the problem is here. This is theta, and so that must make, sorry, my screen froze. That must make this angle theta. This angle is 90. That would make this angle 90 minus theta. Okay, and so as far as components, I'll write those in green. So that is f cosine theta, and you've got one f sine theta that points up. And then for the normal, it would be the cosine of 90 minus theta, but that's the same thing as n times the sine of theta. Okay, and then that means that the upward component of the normal force, that's n cosine theta. Okay, so now everything's in nice, neat components, so I can come down and I can write my Newton's laws. So in the centripetal direction, sum of the forces equals, now I want to accelerate inward, so I'll call the left positive, plus fc cosine theta minus n sine theta. That has to equal the centripetal acceleration. So that has to equal m v squared over r. Okay, let's just move this over. Okay, and so now we'll write the forces in the y direction. So n cosine theta, that points up. F sine theta, that points up. And mg points down. And all of that has to be equal to 0. Okay, so the only thing we need to do is we need to know what this r guy is. We don't know the value of r, so we have to solve for that. And so they talk about the cone and they make a big deal about it, but the truth is we have some hypotenuse d, and this angle is theta, and the distance from the center of the cone is this, which is just d cosine theta. Okay, so if we make this substitution and this substitution, okay, then we'll end up with, let's see, mu times the normal times cosine theta minus n sine theta equals mv squared over d cosine theta. And then on this side we have n cosine theta plus mu times the normal times sine theta minus mg equals 0. Okay? Believe it or not, the physics is done. This is just a giant algebra problem at this point. It's not terrible algebra, but it's not pleasant algebra either. So what I'll do at this point is I'll pause the video. I'll do the algebra and you can take a look at it, and then we'll discuss the result we get. Okay, so blah, 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 algebra. You end up with a final answer of 3.62. Maybe one thing that's worth pointing out is it seemed like I had 3 unknowns. It seemed like I didn't know what the normal force was, and I didn't know m. They don't tell me m in the problem. And they also were pretending that I don't know v. So it seems like I have 3 equations and 3 unknowns. But the m ends up canceling. And so maybe the lesson to learn from that is work your algebra as much as you can and keep your fingers crossed and hope that it will work out. And generally it does. Look, so the key takeaway here is, okay, the maximum velocity friction can have. So using the maximum force that friction can provide, which is mu times the normal, that's maximum, right? Then that gives me a speed of 3.62. In the problem, they say he's going 3.75. What that means is that friction is not strong enough to keep the boy accelerating toward the center of the circle, and so the boy will spiral outward. In other words, he doesn't have that perfect speed to keep him in a circle, and in this context, spiral outward means he's going to start sliding down the ramp. So this is impossible. Okay, so algebra is ugly, but the thing I want you to take away from this is, number one, there's no such thing as centripetal force. There's just forces that are in the centripetal direction. And if you want to move in a circle, you need that to be your centripetal acceleration. And also, this crazy complicated problem, the worst thing you can do with it is sit down and think about it. Draw your free body. There was only 3 forces. Break them into components, and then just think of yourself like a machine. You're a machine that converts free body diagrams into equations, and then you grind through algebra. You can think about why it does or doesn't make sense at the end of it. Okay, I know that's not a fun thing to hear, but that's the most successful philosophy for solving these kinds of problems. Okay, if you're confused about this, you can post on the homework discussion board.